In this video, we are going to do something what may look like super simple or something trivial, and maybe people may ask why I should do this. Because we are going to measure resistance of traces. Is it correct, Eric?
Yep. So we're going to do something that you're exactly right. I mean, you say, oh, we're going to measure the resistance of a trace. People say, oh, that's so easy. Why do I have to worry about it? What's important about it? And if you've never done it before, you will be astonished at the results, number one. Number two, I'm going to show you a common mistake that is done in the measurements and introduces a significant measurement artifact and how to get around that artifact so you can get a more accurate value of the resistance of a trace. And then if we have a little bit of time, we'll blow traces up and we'll look to see how much current can you actually put through a circuit board trace.
Okay, I'm very curious about the last part. But
And sorry, yeah.
yeah, before we move to the measurements, I would like to also point out this may be important also because sometimes in some PCBs we need to we need to measure currents and very precisely. So maybe these measurements, what we are going to do, can help people to understand how to maybe do a PCB layout a little bit better, how to route the traces, or is it correct?
And while we're talking about the application and the so what, I think the real value is when you're designing routing for power traces. Knowing what the resistance is of the trace, the path, and knowing how much current you can put in it safely before the self-heating blows it up. Knowing those numbers, I think, are really important to evaluate best design practices for power path. And that's one of the things that we'll be looking at here as well.
Okay, so let's start. Let's have a look how
Okay.
much current we can handle and what is the resistance of these
Right.
traces.
So first, let's talk about measuring the resistance of a trace. We're going to come to my lab here. So we're in my lab here, and I have set up a test board that we use in one of my classes that is designed to both measure the resistance of different line width traces. They're all 1 inch long. So the number we'll get is the resistance per inch. They're different line widths. I got 6 mils up to 100 mils, and they're just replicated down here, so we have more variety to use. They're set up in a specific way in order to use a standard digital multimeter as an ohm meter to measure the resistance. And they're also set up to use the special technique I'm introducing, the 4-wire method, and why it's so important. And they're also set up, we can measure the resistance, we can also crank up the current through them and look to see what happens to the trace. Now, before we actually do the measurement, I always like to start out, I have my rule number 9 that I think is one of the most important rules in engineering, which is before you do a measurement, anticipate the results. And so we're going to measure the resistance of a trace. So it's important to be able to estimate, okay, what is the resistance of a trace? And so I'm going to just show you really, really briefly how we estimate the resistance of a trace, and we can do it in a really simple way. And I'm going to draw a little picture here of a trace. So here's the view of a trace,
Mm-hmm.
and it's got some thickness to it. It's got a line width, and it's got some length. And the resistance is going to be, there's a term that's a measure of the material property of copper, the bulk resistivity, times the length divided by the cross-sectional area. And the cross-sectional area is the width times the height. So it's the thickness times the width. And so that's the bulk, that is the series resistance of that trace given the length of the trace. And we can simplify it a little bit, make it easy to understand, because if we're talking about a layer on a circuit board, and we have copper foil on that circuit board, everywhere on that surface, for any place we look, for any trace we build, the bulk resistivity and the thickness are exactly the same. So I'm going to write this as bulk resistivity over the thickness times the length of the trace over the width of the trace. And so you tell this number is fixed. It's
Mm-hmm.
the same bulk resistance, same thickness. You tell me what the length of the trace is and the width, and I'll tell you what the resistance of that trace is. And the reason I wrote it this way is because this is a special term, because it's the same for every single trace we draw on that layer. We're going to pull that out and we're going to give it a special name. And now, if let's look at the second term here, the length over the width. If I'm going to do a top view here. So here's our trace. And I'm going to draw on this trace. I'm going to divide it up into squares so that the length is equal to the width. And in this case here, so here's the width, here's the width. So these are all squares. And I can count, let's see, the ratio of the length to the width is literally how many squares do I fit? There's 1, 2, 3, 4, 5 squares in this case. Well, if the length equals the width, this ratio is 1. And so the resistance of 1 square, so here's that 1 square. The resistance of 1 square, if I send current through this square, and I measure the resistance from this side to this side of that square, the resistance is this first term here times 1. And so that is the resistance of 1 square. And that is literally the bulk resistivity of the thickness. And we call that the resistance of a square, or the sheet resistance.
Mm-hmm.
And the units are going to be the ohms per square.
Mm-hmm.
Well, the crazy thing is, and this is, I don't know, I think it's counterintuitive. If I have a square that is 10 mils on a side, and I measure the resistance from one edge to the other edge, I'm going to get, and so let's put in the numbers here so we know what that number is. For bulk resistivity of copper and the thickness for 1 ounce copper, I'll just tell you the number, 0.5 milliohms per square for 1 ounce copper.
Mm-hmm.
And really good number to remember because all 1 ounce copper is about that number. And for half ounce copper, it's half is the thickness is half the thickness, and so this gets half smaller, this gets twice as big. So it's going to be 1 milliohm per square. Two really important numbers to remember, because we're going to use them
Mm-hmm.
over and over again for half ounce copper. Now, this is making an important assumption. It's making the assumption that the bulk resistivity is for oxygen-free copper, and the thickness is for 1 ounce copper, it's 34 microns, and for half ounce copper, it's 17 microns. So given those assumptions, then these are the values for the we call it the sheet resistance of the copper. Here's the crazy thing. The resistance of a trace now, I'm going to rewrite it as it's the sheet resistance per square, times the number of squares. If I have 1 square, the resistance of that square from edge to edge is just that sheet resistance, half a milliohm or 1 milliohm, depending on the thickness of the copper. That means if it's 10 mils on a side, or if it's 10 inches on a side, edge to edge, I still have 1 square from one end to the end. The trace resistance is exactly the same. That, I think, is startling. A 10 mil, tiny little square, 10 mils on a side, measured edge to edge, is, if it's 1 ounce copper, is a half a milliohm. A 10-inch long square, 10 inches on a side, measured edge to edge, is also a half a milliohm of resistance. And that's because you think, well, if I make it 10 inches longer, it's going to get a lot higher resistance, but I make it 10 inches wider, those two effects cancel out and it's the same resistance. So now we have a way of estimating the resistance of a trace. All we need to know is what layer it is, what the thickness is of the copper, half ounce, 1 ounce, and how many squares, the length over the width. That's counting how many squares there are.
Mm-hmm.
So let's take a look at the first example that I've got here. So this is a trace that's 100 mils wide, 1 inch long. And so we would expect the resistance of that trace to be, and it's on the top layer, and so that's a half ounce copper, roughly. We'd expect it to be 0.5 milliohms per square. To make sure we get that visible here. It'd be half a million per square times, let's see, how many squares are there? Well, it's 1 inch long and it's 0.1 inch wide, so that's 10. And so we would expect this to be 10 times this 5 milliohms.
Yeah, it looks like we can fit 10 widths.
Yeah,
Yeah,
exactly. And it's exactly that. From here to here is 1 inch, 100 mils wide, so we get
yeah,
10 squares
yeah.
down the line. This means that at a glance, if you can look at your trace and you can estimate with your eye how many squares you can fit, that times the sheet resistance is the resistance of a trace. Trivial to do in our head. So we expect for this trace 5 milliohms. So let's measure it. And so I've instrumented this board so we have little holes to clip the leads. I've got my digital multimeter set for volts right now. We're going to change it to ohms and we're going to measure that resistance. So we're going to measure here and then this piece over here. And so I'm lying a little bit. It's 5 milliohms for this. And then what's this going to be? Now we know the trick. I can estimate how many squares do I have in this path. And this turns out to be, it's about 1/4 of an inch wide, and it's about 1¼ inches long. I'm sorry, it's 1.5 inches long. So 1/4 inch wide. So that's 6 squares. So what's the resistance of this piece here? It's 6 squares times half a million per square. That's 3 milliohms. So really, I would expect to see from here all the way down to here, I would expect to see 3 milliohms plus 5, 8 milliohms, about 10 milliohms of resistance. Okay, so let's
I
do
have
that
a
measurement.
question
Sorry.
before we do
Yeah,
the measurement. What about the
yeah.
resistance of the wires?
Oh, you're ahead of me. That's one of the problems, the artifacts that we're going to encounter, and that's what I'm going to show you. So this
Okay,
is why this is why rule number 9 is so important. Estimating what you expect to see helps evaluate the results. It's the first consistency test we're going to do when we look at a
okay,
measurement.
so let's
So
measure it.
so you're ahead of me. So now let's turn on, and I'm going to switch to 2 ohms. So I set the 2 wire resistance measurement. Now remember, we expected to see a value of about 10 milliohms. And on the scale here, you can see it's auto scale. So this is as sensitive it gets. This is in units of ohms. So here's 1 ohm over here. And so this is in milliohms over here. So it's 75 milliohms. Wait a minute. I thought it would be 10 milliohms. It's 76 milliohms, 75 milliohms. Oh my gosh, that's a lot higher than I expected. And if you hadn't done the estimate, if you didn't know what to expect, you would say, okay, 75 milliohms, that's really low resistance. That's because it's a wide line. Okay, so a wide line like that is going to be 75 milliohms. But we know it should be less than 10 milliohms, so we're way off. Why is that? Well, you are exactly right. What about the resistance of all these wires here? And so maybe we should measure the resistance of the wires and see how much that contribution is.
Yeah,
So let's go ahead and do that. So I'm going to disconnect these guys. We're going to measure it from one to the other, and let's see what that is. So it's auto scaling, sending current. Wait a minute, that's 69, 70. Oh, boy, it's moving around a little bit because after all, any instrument, any digital multimeter, there's an absolute accuracy and there's also an uncertainty. And usually it's rated for plus or minus 2 digits or 2 numbers in the last digit.
mm-hmm,
So this is 70 70 milliohms plus or minus 2 milliohms
mm-hmm.
is roughly the value. There's always an uncertainty to every measurement. The absolute accuracy of this guy here is 0.1% absolute accuracy. And so I think whatever is coming out of the front here, the resistance that I connect here, I think it's probably accurate to, maybe 2 or 3 milliohms, something like that. But it's about 70 milliohms, plus or minus 2 or 3 milliohms there. Oh my gosh, that was just about what we measured, right? So most of that resistance we measured is all the wire resistance. And let's see, so it's about 70 milliohms now. If I disconnect it and then I just connect it again, let's see what we get. It's going to auto scale and about the same. So if I remember that number, I can subtract it off and then see what I have left, right? So let's do that. And we have a button here, it's called null, that will take the current measurement, put it in memory, and subtract that from all the other measurements. So let's do that. So here's the value that it's subtracting off. And this is the value that it measures directly. It subtracts off that 69
Okay,
milliohms. Here's the residual measurement. Okay, so it's showing us the raw measurement and after it did the zero subtraction.
Calibrated.
Zero. I'm not sure I would say calibrated, but it's subtracting off the offset.
Okay, okay, I understand.
So now let's remeasure our trace. Let's do it from this side here. So I got that guy in there, and oops, we'll measure from here. And let's see what we got. So the raw measurement is about what we saw before, about 75, 74 milliohms. And look at that. Oh my gosh. It's about, unfortunately, the resolution of this ohmmeter is, again, like I said, it's the last digits like plus or minus 2. And so it's about 5 milliohms plus or minus 2. That's like 40% uncertainty. That's huge. Oh my gosh, I really would like to get a more accurate value with less uncertainty than that. But it's about what we expect. So actually, we said it was 5 plus, it's about 8 milliohms. So it's within that range of 8 milliohms. It's plus or minus that, 2 or 3 milliohms there. It's still a huge uncertainty. Boy, it'd be nice if, and then, I have the other problem of, these wires, they had 70 milliohms of resistance. There's also contact resistance at the tips here when I connect them in, and that contact resistance can vary a bit as well. Look at that. I
Yeah,
just
yeah,
I
yeah.
just did it again, and oh my gosh, now I don't even see that much. So when I'm measuring a small resistance, first of all, this ohmmeter it's a great ohmmeter. It's a wonderful box, but it can only measure in the plus or minus like 2, 3 milliohm kind of range. And that's the uncertainty, and that's the order of the number that I'm trying to measure. And I've got the resistance of the wire to worry about as well, and the contact resistance of the lead that I'm making down here. So every time I connect it in, I get a slightly different number because of the contact resistance and the small numbers I'm trying to measure. One way around that is a technique called four-wire method. And here's the problem. Now we're going to talk about the measurement. So I've got some component here, a wire and our trace, and I want to measure that resistance. What we've been doing here, so fundamentally, how do you measure a resistance? And so the way it works is there's some voltage source here, and I'm going to put an ammeter in series. I'm going to measure the current, and and then I'm going to come along and I'm going to measure the voltage. And all this is inside the ohmmeter. And so it's going to output some current. It's going to measure that current. It's going to measure the voltage on the inside here. And it's going to tell me what the resistance literally is, the voltage I measured divided by the current. The problem is I've got the lead resistance here, and I've got the contact resistance at the joints. And so the equivalent circuit of that is really, I've got the resistance of the lead, I've got the resistance of the DUT that I care about. I've got some contact resistance here, some contact resistance here. I've got the lead resistance here, and then it comes back here. And so I'm measuring this equivalent resistance. And so all I want is this. I don't care about the lead resistance or the contact resistance. I just want the resistance of the device. And so when I do we call this a two-wire, distinguished from four-wire. Do a two-wire measurement, all I measure is the result. And so my equivalent resistance is going to be the two lead resistances, two contact resistances, plus the device under test. That's the problem. I don't care about these guys. I want this. And in our example here, the resistance of the thing I care about is a tiny fraction of these resistances. And so the technique we're going to use is we're going to separate out the voltage and the current measurement to measure. We're going to still force current through the whole thing. And of course, they're in series. So every element in series has the same current going through it. So if we measure the current here, we know the current that goes through all of these and the current through the dot. But I want to come over here and I want to measure the voltage just across the dot. And now the resistance of the dot is going to be the voltage across the dot divided by the current through it. And that's what the 4-wire does. And to do that, we're going to use in the digital multimeter, this is going to drive the current. There's an ammeter on the inside. It's going to measure that current. And these two probes are going to measure the voltage across the wire. So I'm going to turn off the null. We don't need that anymore. We go back to the resistance. I'm going to leave this up because this is going to send current through the wide trace. There's no place else for it to go. It's going to go through here and come out the other end. So that's where the current's going to flow. And we're going to use another pair of leads to measure the voltage. I want to measure the voltage just across this wire. And so I'm going to look from this end, and I can't measure it from here. So think about the current. It's going to flow through here, da-da, da-da, da-da. It's going to go through here. I may get a voltage drop here. So what's the voltage drop from this region to this region in the wide trace? What's that voltage drop going to be? It's a trick question, because the only way you get a voltage drop through a resistive element is if there's current flowing through it. If there's no current, there's no voltage drop. So that means that the current's flowing through here to here. There's no current in this path here. That means there's no voltage change. So the voltage I measured down here is exactly the same as the voltage here. And so by forcing current through this path and measuring from here to here, I'm going to be measuring the voltage just across this segment, which is exactly what I want. That's going to be the 5 milliamps.
That's nice trick.
Isn't that a nice trick? It's one of those, George Polya, a mathematician at Stanford, he used to say, a method is a trick that works more than once. And so this is a very important method. So we're going to measure the voltage across the high side. And we're going to measure here's my other lead. We're going to measure the voltage across the low side. Now, this is still set up for 2-wire. So we're just measuring that same 72 milliohms, which is the combination of the wire through here and through here. So that's going to be the wire plus the 10 ohms. That's the total resistance. Now, when we push the 4-wire, we're going to eliminate, I don't care what this resistance through the wire is. I don't care what the contact resistance. We're going to measure the current internally here. I don't know what it is, but it's about 100 milliamps. We're going to send the current through here, and we're going to measure the voltage across here. So let's do that. So I'm going to go to Shift and 4-wire, and now it says 4-wire, and look at that. What did we expect to see? We expected to see about 5 milliohms because we're just talking about this guy here. We expect about 5 milliohms. We're getting 3, 2, remember it's plus and minus about 2 or 3 digits there. We are at the absolute limit of what this poor multimeter can do. If we want to measure the resistance of this trace, 5 milliohms, we're close, but we are at the limit to what this poor guy can do. It just can't get lower than a few milliohms, and that's the thing we're trying to measure. Even with the 4-wire method, we've eliminated the lead resistance, we've eliminated the contact resistance, but this poor little guy just can't do any better. So I'm going to show you another technique that's going to let us measure really low resistances. And this is a method, we use this, I taught sophomore circuits last year, and they do take-home labs, and this is a lab that they did where they actually measured the resistance of a 22 gauge wire. It's like 15 milliohms per foot, and they were able to measure it really easily in their home dorm rooms with their little kits. So it's a really simple method. And here's what we're going to do. We're going to do exactly the same thing that this guy does.
I'm going to guess. Can I guess?
Yeah. Yeah.
Are we going to put there more current? I don't know.
You bet. Exactly right. Because here is the relationship. This tells us how we're going to do the measurement. We're going to measure, if we want to measure a really small resistance here, we have to be able to measure a really small voltage and generate high current. And so the way we measure the low resistance is we send in large current and we measure small voltages. And that's one of the values of this little guy here is he's a pretty good ohmmeter, but he's a really good voltmeter. So we're going to set him up. We're going to turn off the 2-wire. We're going to measure voltage. And now we're going to do exactly the same thing. We're going to measure the voltage across these leads. That's the voltage from here to here, and we're gonna force current through the guy,
Mm-hmm.
and we're gonna. So I have a power supply here. This is a constant current, constant voltage power supply. We're gonna set a current in it. We're gonna start with 100 milliamps, and so we're gonna send a current through here, and it's gonna go from the bottom, and the voltmeter, the digital multimeter set as a voltmeter, has really high impedance. In fact, here it says 10 mega ohms. So there's 10 mega ohms going here. So that's effectively zero compared to the milliohm of resistance. So when I send current through this trace, it's going to go here and it's going to go here. When it goes here, it goes into the multimeter, and there's 10 mega ohms. There's no current going through there. I'm going to ignore that. But the current's going to flow this way and coming out. So it's the same as we had before. Current path is coming up and over, and I'm going to measure the voltage from this side to right here
Mm-hmm.
on that side. So let's do that. So I'm going to set up my power source here, and I just want to make sure it's off, just to make sure I'm not going to blow something up. And now we're ready to turn it on. And I set it for 100 milliamps, zero point 0.1 amp. And I like doing it because in nice multiples of ones and tens, because now the resistance of the dot, that wire, is going to be whatever voltage I measure divided by 0.1 amp,
Mm-hmm.
which is that voltage measured in volts times 10 here. And so it's going to be the voltage we measure is 5 milliohms divided by 10. That's the half a millivolt. 500 500 microvolts is what we should measure. So let's turn it on, see what we get. So here we go. And hey, look at that. We get 0.1 amps coming through here. And look at what we're measuring. We're measuring 0.39, about 0.4 millivolts. That means, so what we measure is 0.4 times 10. That's 4 milliohms. We
Mm-hmm.
expected about 5.
Mm-hmm.
We're measuring 4. And look at that. With 0.1 amp, we can see the last digit here is where the noise is, plus or minus a couple of microvolts. That means right now it's plus or minus, tens of micro ohms of resolution. So even with 100 milliamps, we get much smaller resolution, finer resolution with this method than we could with this guy all by himself.
Mm-hmm.
And and you could literally use almost any digital multimeter and any power supply to do this measurement. You don't need a really fancy high-end multimeter to do it.
But
So
you need the
that's,
power supply, special power supply.
well, you do. But you know what? I bought this off of Amazon for $60. So not very expensive. And it goes up to 10 amps. And we're gonna crank this up a little bit to measure the resistance even better. Because this is 1 amp. I'm sorry, a tenth of an amp.
Yes.
If we get an amp, we ought to get 3.9 millivolts,
Okay. I'm
which would
curious.
be if this is 1 in the denominator, then the resistance is literally the voltage in millivolts in ohms. So let's crank it up. So I'm going to move it to this one, and we're going to crank it up to, okay, we got 1 amp going through it. And look at that. It's
Mm-hmm.
3.8 millivolts. And with 1 amp down here, 3.8 millivolts is 3.8 milliohms. Now, we thought it was going to be 5. It's 3.8. How come it's lower than when we expected? Why is that? Is something wrong in our calculation? Well, remember, when we did this estimate, we assumed 1 ounce copper, and we assumed oxygen-free copper resistivity. And this is top layer, and so they plated this. So it's probably 1 ounce with the plating. So I don't know what the thickness is, but I think it's thicker than 1 ounce copper, and that would pull the resistance down. And so this value of 3.8 milliohms for the 100 squares is probably a good number. It's just that we don't really know what the sheet resistance is. In fact, this is one way of estimating what the sheet resistance is. But while we're here, let's just see how consistent is the measurement. I have a trace over here that is 100 mils wide and 1 inch long. I have an identical trace here. Let's just measure this guy's resistance, see how close it
Okay.
is. Remember the 3.8 milliohms. Let's go over to the other side. And first, let's just redo this measurement just to see how reproducible is it. Because it shouldn't depend on the contact resistance or anything else. We're at 1 amp. There's 3.8 million, right? Very consistent. Let's just go to the other side, and we will do the same connection here. And this measurement, because it is forcing the current, independent of the wire resistance, independent of the contact resistance, it is the same current. We're measuring that voltage, look at 3.8 milliohms. So same resistance for that trace, very consistent. Now, let's take a look at, that was for a relatively wide trace, 100 mils. Let's take a look at another trace. We've
Smallest
got
one.
one here. Sorry, huh?
Smallest one. Let's do the smallest one.
The smallest one, 6 mils. And so what do we expect? What's the sheet resistance for the 6 mil one? Well, first off, if it's really sheet resistance of 0.5 milliohms per square, then the resistance of this 6 mil trace should be, let's see, it's 6 mils. It's going to be 0.5 milliohms per square times the number of squares. So what's that? It's 1 inch divided by 0.06 inches. And this is, it's 16 squares. And 16 times 5 is about 80. So it's about 80 milliohms is what we expect, right?
Okay.
This is
I trust you.
1 inch over, oh, I'm sorry. I'm doing this too fast here. And my students always, I tell my students I make mistakes on purpose for them to catch it, but sometimes they don't catch it. But so it's 6 mils, so it's 0.006. So this is 160, 1 over 0.006, 160. 0.5 times 160, that's the 80 milliohms. So we expect the resistance for the 6 mil wide trace about 80 milliohms. So let's do that measurement. So we're going to take our current, and I'm going to turn the current off for now. We're going to send the current from, let's see, we'll make this the high side, make this the low side. Oops. But yeah, it doesn't really matter. This is the yellow is the low side. This is the high side. We'll measure the voltage on the high side with the voltmeter. We'll measure the voltage on the low side with the voltmeter. There we are. We're connected up. And now let's, instead of an amp, because that's 6 mils, that's really narrow, right? That's like the cross-sectional area is thinner than a human hair. So that's really, 1 amp, uh-oh, that may blow it up. So let's drop that current down. So let's go to 0.1, like we did before.
Yeah,
Now we
because if
expect
it's 80, then yeah,
yeah,
we can
right.
go
So
10
we
times
expect,
lower.
yeah, exactly. So we expect to measure the resistance of that wire is going to be the voltage we measure divided by the current, which is 0.1 amp. So that's going to be the measured voltage times 10. And so the measured voltage, if it's 80 milliohms, or 80 milliohms divided by 10, that's 8 millivolts. Okay, so we expect about 8 millivolts. Let's see what we get. So I'm going to turn the current on. It's on, and there we are, 1.1 amp. And it's not 8 millivolts, it's 5.7. Well, that's because, we saw before, the sheet resistance is lower than what we expect for 1 ounce, probably because it's thicker than 1 ounce copper. So, but it's 5.7 milliohms. That's, in the ballpark of what we expect. I think this is a pretty accurate number because I think the uncertainty in the current is about 1%. And I think the accuracy of the voltage is better than 1%. It's plus or minus the last couple digits over here. So I think that this is accurate to about 1%. And so I think it's a good number. It's just that lower than we expect because the sheet resistance is smaller than our simple estimate of 0.5 milliohm. And I have, see, where did I put my other board? I have another board here. And let's just go ahead and measure. I've got the similar trace over here. Let's see how this board, identical board, same lot that we got from the vendor. Let's see how this resistance compares to this one. So remember this number, 5.76.
Mm-hmm.
And now let's just connect it up. And we're going to use the other side here because I already blew up some traces on
Yeah,
this
I
one.
see there are some black
Yeah, yeah, and we'll do that in
spots.
this one here. It's that'll be the next thing that we do right after we finish this measurement. And let's see, so it should be, what was it? 5.67. Oh wait, that's 7.15. So depending on the board that we've got, and depending on the lot and the processing it went through, this is a lot closer to what we expected of the 8 millivolts for 80 milliohms, because I think it's not as overplated
Mm-hmm.
as the other one. It
Is
could
this
also be the
different
edge. Huh?
PCB manufacturer or it's the same PCB
Nope.
manufacturer?
Same fab vendor. It could also be, so this is a 6 mil wide trace.
Mm-hmm.
It could also be an etch back. It could be that in this board that had the low resistance, it wasn't really 6 mils. It might have been over plated up plus a little wider because you get plating on the edge of the trace there. So this could have been overplated. This could have been etched back a little bit more.
Oh, this
So
is
hard to
interesting.
know. Hard to know unless we do a cross section or we do a measurement of the dimensions.
So this way you
Um,
can also kind of verify how good the PCB manufacturer or how consistent the PCB
How
manufacturer is.
consistent, exactly. How consistent. So measuring sheet resistance in general is a really important number to know for your board. And there's some techniques that we could literally use that 100 mil wide trace to do that because that's 10 squares. We measured a resistance of like 3.5 milliohms for 10 squares. Hey, that's 0.35 milliohms per square. That's the sheet resistance of that board. And that's one way of getting it. Do the same thing. You want to do it on because of the potential of etch back that you don't know about. You want to do it on a wide line because the percent impact from etch back
Mm-hmm.
is much less on a
Mm-hmm.
wide line. But that means you're measuring really low resistance. That's where you want to use this technique of
Mm-hmm.
forcing a high current and separately measuring the voltage. Well, while I have this set up, let's blow a trace up. Let's ask that question. Here's a 6 mil wide line. It's 80 milliohms. We're putting a tenth of an amp through it. We get 7 millivolts across it. Let's ask how much current can we put through that trace before we blow it up? And what would be your guess?
Mm-hmm.
Now, keep in mind the cross-sectional area of the 6 mil wide line is thinner, a smaller cross-sectional area than a human hair. How much current can we put through a wire? That's the dimension of a human hair.
I know what the answer is because I already done this experiment.
Yep, yep.
It was one
I
of the
think it is.
experiments what I always wanted to try, and I still remember the smell of my lab. Like,
Yeah, it is, I think, one of those really important measurements that every engineer needs to do to get a feel for it. And it's so startling. And that's why in the PCB class that we teach, every student gets to blow up traces. So let's see. Now, IPC has a couple different specs that allow you to estimate about what resistance you can put through or what current you can put through a wire without blowing it up. They're really rough approximations because it depends so much on the thermal environment, the layer stack, all those kinds of things. But if you use the IPC spec, it says, okay, 1 ounce copper, 6 mil wide, surface trace, it's something under about 3 amps. Um, no, I'm sorry, I think their spec is 1 amp. And it's a very conservative spec. And it depends so much on the thermal environment. But even 1 amp, my gosh, that's a huge amount of current through a narrow trace. Can you really do that? Well, we've got 100 milliamps. Let's crank her up. So I'm gonna switch the digit here. I'm gonna crank her up. So there's 0.1 amp. Let's get up to 1 amp. Here's the IPC spec. And we have 10 times the voltage. And here it is. And if you notice that voltage, it's going up a little bit, just a tiny, because we have such a great voltmeter here, and we can read so many digits here. You can see it's going up a little bit. It's not constant. How come? If I touch the wire, what do you think is going to happen if I touch the wire? What do you think is
you are
going to happen
going
to
to
the?
cool it down,
Very good.
so resistance is
And
going to change.
it's going to go down. So for copper, the higher the temperature, the higher the resistance. So I'm heating it up a little bit. That's why the voltage is going up. The current's constant at 1 amp. I'm heating it up. The resistance going up. The voltage across it's going up. So if I touch it, I'm going to cool it, and it'll go down. It's going up. How come? Not what I expected.
You are
How
heating
come?
it up.
Now, above I heated it up above
No, you
the
maybe you
temperature
changed
that
resistance. I don't know.
my body temperature was warmer than the temperature of the wire. Because I touch this, I don't feel anything. And
Okay.
I'm warming up, I'm warming up. So 1 amp is not enough current to even get it, much above ambient temperature.
Yeah, I would like to point
So,
out this actually because
yeah,
there are a number of calculators which can help us to estimate what is the maximum current through a trace.
yes,
But usually in these calculators, we we need to pay attention what temperature rise is set in these calculators because
right.
normally this value is very low, so that's why also the maximum current for traces calculated with these calculators is much lower than the current which will actually blow up the trace.
Right. And not only that, but so I use the Saturn PCB tool a lot because it's really simple, easy to use. It has the IPC spec in there to estimate for it. It depends on the temperature rise that you care about. It depends on the thermal environment of the trace. And so it's only meant as a rough guideline. And there's a lot of margin built into it. And so just as the example, here we are with 1 amp through the 6 mil line. I don't feel any temperature rise. And in fact, my body temperature is warmer than the temperature at which the wire's at. So let's crank her up. I'm gonna go up to 2 amps. And so we're at, well, wait a minute. Look at that. It's still increasing. It's 5.2, it's 152 millivolts, 153. It's going up because now it's actually self-heating and it's getting a little warmer. Now, if I touch it, I might cool it and I drop the temperature down.
Mm-hmm.
I let it self-heat, it goes up, and then it's reaching equilibrium now, so it's not going to go up very much. And now I touch it, I cool it, and it goes down. And I can feel it's a little bit warm. 2 amps, it's a little bit warm. Okay, let's go up to 3 amps. Three amps. Okay, now 3 amps, it's 256, 257, 258. Oh my gosh, it's going up. 260, and ow, that's hot. So 3 amps, it's noticeably hot. And when I touch it, I cool it, I suck the heat off, drop way down, and now it's healthy heating, and it's going up, and it's going up. And it'll reach an equilibrium as the power dissipated, or the power consumed in the wire matches the power dissipated into the air. But it's gonna get warmer. Let's see if we can't get it into thermal runaway. Thermal runaway means it's so hot that it gets hotter. The resistance increases. It's I squared R. The I is constant. R gets bigger. Power consumed gets bigger. It heats up more. Resistance increases more. It gets even more power consumed, and it just cascades and then it blows up. So let's increase that current. I'm gonna get that digit. And so now we're up to 3.5 amps. Think about 3.5 amps through that tiny little 6 mil wide line. And the resistance is increasing. If I touch it, ow, that's hot. I'm gonna touch it much more. We watch that voltage increasing, slowly increasing, 3.5 amps. It'll probably reach equilibrium here. It's getting a little bit bigger. The temperature is getting higher, the resistance is getting higher, the power consumed, I squared R is getting bigger, power consumed is getting bigger. It's getting hotter, but it's pretty stable. Let's
Mm-hmm.
increase it
So
some more.
I'm curious. So when we reach the thermal away, we will see
Yeah,
how this resistance will actually
yeah,
go up.
let's do that. So here's 3.6, here's 3.7 amps, and you can see it starting to increase faster.
Mm-hmm.
Let's go to 3.8, and
Mm-hmm.
now
Mm-hmm.
it's increasing faster. I'm not sure if we're in thermal runaway yet because it's kind of stabilizing here. We'd have to kind of plot this to see what the curve is. When it starts increasing kind of exponentially,
Mm-hmm.
that's thermal runaway. So if we set her long enough, maybe in still air, maybe it'll reach thermal runaway. Let's, oops, I didn't want to do that. I wanted to get my digits right here. Okay, so we're at
Okay.
3.9 and okay, look at that. So 4.6, 4.7. Yeah, it's pretty stable. Ow, that's hot. Getting hot. And so it's still pretty stable. 3.9. Okay, let's really crank it up. Let's go to 4 amps. Okay, 4 amps. Oh, come on, let's do it some more. This is why my students love this because they get to blow things up. So let's go up to 4 amps, 4.1 amp. It's 4.1 amp.
Oh,
And so that number is increasing. We're going to see that number increase faster. No, not quite in. I mean, if we left it here, we'd be in thermal runaway. Let's do a little bit more. It's 4.2 amps,
yeah,
4.3
yeah, yeah, yeah,
amps.
yeah.
Ah,
Now,
there we
see.
go. You think now? Okay. 5. Okay, it's increasing faster, faster. And it's steady increase. It's not, oh, well, just
Yeah, it's
barely. I don't
yeah,
have
yeah.
that
It's
much
getting
patience.
faster, faster.
Yeah, let's just do a little bit more. It's 4.4 amps.
Okay. Is it changing? Oh, yeah,
Okay,
yeah,
can you
yeah.
see the
It's changing.
smoke?
Yeah, yeah, yeah.
Can you see the smoke
Yes.
coming off of it? So now it's thermal runaway. Now it'll just self-heat because the temperature is going up, the resistance is going up, power consumed is going up. It's getting hotter and hotter. I can smell it. You can see the starting to glow.
Yeah,
You
yeah.
can see the smoke coming off of it. Let me see. Can I get that a little better
Yeah, I
for
can
you?
see the glow. I can see the glow.
Yeah.
Yeah, yeah, yeah.
Oh, it's a wow.
Oh,
There it
it
went.
was there.
Darn. Okay. So I'm gonna turn my power supply off here. Yeah.
And your air
So
conditioner.
yeah, well, you know what? I have to be careful where I do this experiment because I don't want to do it under the fire detector, the smoke detector. So that's think about that. We were at 4.4 amps before we went into thermal runaway. The IPC spec says now you don't want to run 4 amps through a 6 mil wide trace. That's too much risk, but you can easily run 1 amp through it without any danger. And that just illustrates what I find incredibly startling, that a 6 mil wide line, something that is thinner cross section than the human hair, you can easily put an amp of current through it. And we know what the resistance is. So when people say, "Oh, narrow lines, they have a lot of resistance," well, a lot is a relative term. Put in the numbers. We just saw a 6 mil wide line, 80 milliohms per inch. Is that a lot or a little? Well, it depends on the application. If I'm putting an amp through it, we saw 80 mils, 80 milliohm per inch. We saw that was 80 millivolts. Is that a lot or a little? When my power supply is a 5-volt supply, if I put an amp through it and I have 80 milliohms, out of 5 volts, it's 80 millivolts. It's not very much, but that's a 6 mil wide line. I'm not going to use a 6 mil wide line to carry an amp on a power rail.
Hmm.
I'm going to use a 20 mil wide line. 20 mil wide line is going to have it's about 3 times wider. It's going to have 1/3 the resistance. It'll be 25 milliohms of resistance. And we didn't do that test, but in the board, I've got 20 mil and I got 100 mil and I got 10 mil wide lines. And you can put um, about 10 amps through the 20 mil wide line before you get thermal runaway. 10 amps through that 25 mil wide line. So, and the IPC spec says 3 amps as kind of the max. And, that's a very reasonable, safe margined value for max current to put through a 20 mil wide line, 3 amps. So I always say that, if you're designing a board that the worst case current you're going to see on any power rail is 3 amps, then there's no reason not to use 20 mil wide traces to carry the current for distributing power. It's perfectly fine, 20 mil wide line.
That's half
And
millimeter.
signals, Yeah, exactly, half millimeter wide line. Um, and signals, you're never going to get, rarely you're going to get an amp of current through signal lines. That's why 6 mil wide line is perfectly reasonable for signal lines. The resistance, you can calculate what it is. Rarely will that be an issue in signal lines. And when it is, okay, you use a wider line. But unless you have a strong, compelling reason otherwise, signal lines you want to route with as narrow trace as you can for higher interconnect density, easier routing, and power traces, unless you have a strong compelling reason. Otherwise, 20 mils wide is a good line width to use. And again, that compelling reason otherwise is when you put in the numbers if that resistance is too much.
Okay,
So
I think there are a few topics what we could talk about. For example, we were talking about 1 amp, but if we are designing, let's say, processor core power, which is 1 volt, for example, and we can't lose 80 millivolts, and there are going to be,
well,
I don't know, tens or hundreds of amps flowing through
yeah.
this. So
You are absolutely right. When you look at a network processor, a high-end processor, a lot of the Intel, AMD processors in PCs these days, some of them are 100 watts. They're not a lot of voltage, maybe a volt of core voltage, but 100 watts. And a volt supply at dissipating or consuming 100 watts, that's 100 amps. That's a lot of current. You're not going to put 100 amps through a 20 mil wide line. And that is the compelling case for why you want to use power planes. So using power planes, you can distribute the 100 amps. But the point you raise is, well, wait a minute. You got this nice wide plane, it's low resistance, you can carry a lot of current in it, but you have to get that current up to the package, the device, through the vias. And you got limited series resistance and current limitations in the vias. And that's what you design for. So you have power planes and then the vias. And that's for a low-end processor. Some of these AI processors and network processors, we're talking about 500 amps, 1,000 amps. I have seen some, I interviewed some folks on my podcast a couple weeks ago. They're talking about 2,000 amps of
yeah, I
current
think Steve
for one
Sandler
processor.
designed the, yeah.
Yeah, yeah. And so the current distribution approach for 2,000 amps by itself is challenging. And the technique usually is you distribute high voltage, lower current, and then you have point of load VRMs that go from the higher voltage down to the 1 volt for the rail, and that's where you get the current
And
boost
they are
there.
very
Um,
placed very close to the load.
Yeah, yeah. I mean, and precisely for this issue of that series resistance. But not every design needs to be designed for 2,000 amps. That's where putting in the numbers and knowing what the requirements are in your system are so important and designing for that. And that's why it's so important to apply the design principles for each custom design and not use a broad brush sweep and design all systems for 2000 amp delivery.
Okay, I have then another question. So if someone's need to design for higher current, let's say 100 amps,
Yeah.
is it good idea to put the power plane then on multiple layers if we can't have very wide and thick traces?
Yeah, I mean, for 100 amps in that kind of level, it's a question of the sheet resistance is still the same. It's still on the order, if it's 1 ounce copper, half a milliohm per square. And the typical resistance of a via, depending on the dimensions, is on the order of a couple of milliohms. And so most of the resistance is dominated by the vias. And so you want to make sure that rule of thumb, IPC spec, depending on the dimensions of the vias, rule of thumb is roughly about an amp per via as the maximum current. So if you got 100 amps you're going to deliver to a device, you're talking about at least 100 power vias and 100 ground vias just to get the max to not approach that maximum current limit per via. And then as that via makes contact to the power plane and the ground plane, you have to worry about the spreading resistance in the plane. and there's a limit. When you get to that point, there's a limit to what you can do with simple approximations and rules of thumb. That's where a 3D field solver helps you understand what the current paths are. Those 3D current paths in the spreading currents going from the plane into the vias and the distribution of vias, and then going up into the package and through the package. And that's where tools like the ANSYS tool and Hyperlinks tool and ADS have 3D simulators to calculate what that current distribution is and what the IR drops are in all the different locations. And when you get in that 100 amp range for a single device, those tools are essential to give you confidence in, I refer to it as you build a virtual prototype. Before you build the real thing, the real prototype, you build a virtual prototype, and you can do design trade-offs and design analysis so much faster in a virtual prototype than a real prototype. And so you got to use a virtual prototype to do that kind of analysis.
So what do you think if you double the layer, is it going to help, or most of the current is going to flow with the top layer anyway?
Right. Well, we're talking about the DC current.
Yeah.
The power distribution is the DC. There's switching currents because of the IOs, that different issue to have to worry about. But for core logic, it's a DC current that's flowing. And so at DC, the current's going to take the parallel paths, and you're going to have to design, you have to figure out how much current's going to flow, where the voltage regulator modules are going to be, and that's where you need 2-ounce or 4-ounce copper for the planes, multiple power planes, and multiple ground planes as well.
Okay.
Designing that power distribution for the 100 to 500 amp devices is a challenge all by itself. It's not about signal integrity, it's about life at DC, and that has its own set of challenges. And it's these kinds of experiments that we did here help feed your intuition a little bit to give you confidence in the simple approximations, quick estimates, have a rough idea of what's going to be required or where the problems are, and then you apply the 3D simulation tools to help design those virtual prototypes.
And so I have another question. So so often you may see like how does it go, like Kelvin points or something, when you would like to measure current or something.
What we did here, so we did three different measurements. We did the 2-wire method, we did the 4-wire method in the multimeter, and then we used the multimeter as a voltmeter and used our external power supply so we can control the current. I didn't mention it, but the 2-wire, we don't usually call it 2-wire, it's called an ohmmeter. They're traditionally 2-wire. We call it 2-wire to distinguish it from the 4-wire. And 4-wire is another name for the Kelvin method. So it's a method of separating the current paths to a component and the voltage paths that we measure. And it was developed by Lord Kelvin. It was William Thomson in the 1850s. He was made Lord Kelvin because he actually, in the 1850s, the transatlantic cable was laid from UK to Nova Scotia, and it didn't work. There was terrible dispersion and terrible bandwidth. It was like 1 hertz bandwidth in the cable, and they didn't understand why. And William Thomson was brought in. He was Proctor of the Mint, I think, and like chief scientist of England at the time. And he was brought in by Queen Victoria and asked to solve the problem. And he established some fundamental principles about signals on transmission lines and how to measure these really low resistances of the cables. And he developed the 4-wire method, which, because of his work in solving the transatlantic cable, Queen Victoria gave him a lordship, and he lived on the river Kelvin, and he was called Lord Kelvin. And so to this day, we think of him as Lord Kelvin, and he developed the 4-wire method, and was so called the Kelvin method to measure resistance. But it's exactly what we did. We separated the current paths, we separated the voltage paths, and it's a way to measure low resistance.
So this is what sometimes people may see when they are designing, I don't know, some power supplies or something. Sometimes or if they do some special measurements, sometimes in datasheet they say use Kelvin connection. That's what this means.
So when we measure, we use a sense resistor to measure current. You often find you want a low resistor, low value resistor, so that you don't get a large voltage drop. But it means you're going to measure small voltages. And so you'll find a lot of small value sense resistors have 4 leads coming off. They're designed to send the current through 2 leads and measure the voltage across the other 2 leads. And they are using the 4-wire Kelvin method, so that the voltage across that resistor is related to the current, so the current times the resistance, and you're not subject to lead resistance or contact resistance in that sense resistor. So very powerful technique to use a small resistor to measure low currents.
Okay, these are all my questions. Thank you very much,
Okay.
Eric, for this.
Yep. A lot of fun. We'll do another one of these sometime soon, and do another topic related to this.
Yeah, we already scheduled some calls, so if someone is excited to see another video, then, check regularly and there will be something coming.
Okay, sounds good.
Okay,
So
thank you, Eric.
Bye-bye.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedEval online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.